In this lecture, we are going to discuss about Morera's theorem. First is the statement of the theorem. Statement of the theorem. Statement of the theorem. If fz is continuous, continuous in a simply connected domain, simply connected domain, D and integral gamma fz dz is equal to 0, where gamma is rectifiable, closed Jordan curve in D, then fz is analytic. Fz is analytic in D. According to the statement of the theorem, fz is continuous in a simply connected domain D. That is domain without hole, and integral fz dz is equal to 0 over the rectifiable closed Jordan curve in D. Gamma is a closed Jordan curve, rectifiable closed Jordan curve. We have to show that fz is analytic in D. Proof. We consider 2 points z0 and z0 z is a variable point and z0 is a fixed point. Then gamma 1 and gamma 2 b2, gamma 1 and gamma 2 b2 curves, rectifiable curve joining point z0 and z1. Okay, and gamma is the closed curve consisting of gamma 2 minus gamma 2 gamma 1. Here we started from this point to this, so this is this one. So right, let z be any variable point variable point and z0 is z0 be a fixed point in D, fixed point in D. Suppose gamma 1 and gamma 2 be two continuous rectifiable curves, curves in D, joining points z0 to z. Let gamma be the rectifiable closed curve consisting of gamma 1 and minus gamma 2. Okay, then we have, by using the corollary of Cauchy-Grosset theorem, we will get this one. By the corollary of the Cauchy-Grosset theorem, we will get this one. Given this is equal to 0, then right hand side will be equal to 0, then this integral will be equal to minus of this integral. Okay, therefore you should write, therefore, no, first write this integral given integral fz dz is equal to 0. Okay, equal to 0, therefore integral this fz dz is equal to integral gamma 1 fz dz is equal to minus of integral gamma to fz dz. You can also write this, then write this one given. Okay, that means the integral along any rectifiable curve is same. The value of integral is depend upon the point, depend upon the end point, not the not on the curve. So right, that is integral along every, the integral along every, integral along every rectifiable curve, every rectifiable curve in the joining points z naught to z is the same. Okay, it's just same. Next we will going to consider a function fz defined by, consider the function fz defined by fz is equal to z naught z f of w dw. Okay, put this equation 1. The integral 1, as we have already shown here, the value of the integral depend upon the endpoints, not on the curve joining points z naught z. So the value of the integral 1, the value of the integral 1 depends on the endpoints z naught and z. Okay, next, that means we have one fixed point, another variable point. This is our curve. Okay, gamma 1 and gamma 2. Gamma is the curve, gamma 1 plus gamma 2. If we consider any point z plus h, which is the neighborhood of z in the domain D, then so right, if z plus h is any point in the neighborhood of chat, then this function become, then one becomes, replace z by z plus h, we will get f of z plus h is equal to z naught z plus h f of w dw. Put this equation 2 from 2 and 1, from 1 and 2, from 1 and 2, we have, what will be the value of f z plus h minus fz, what is the value? Z naught to z plus h fw dw minus z naught z fw dw. Okay, so using the property of definite integral, we can interchange the limit. This will be positive, so that this will be equal to fz plus h minus fz integral z naught z plus h f of w dw plus if I interchange the limit, this will be z plus z naught, z plus z naught fw dw. This is integral. Now using the property of definite integral, a to b fz dz plus b to c fz dz, integral a to c fz dz. Okay, using this property we will get this as z to z plus h fw dw. Put this equation 3 and wrap this one. Okay, the right hand side of this integral is independent of path, that is path independent. So we consider the line joining still we consider the path of integration to be the straight line joining z to z plus h. So right, since the right hand side of the integral in the equation 3, integral in 3 is path independent, is path independent, is path independent. Therefore it may be taken along the straight line joining z to z plus, along the straight line, along the straight line joining z to z plus h. Okay, so that we have, so that now if we divide right hand side of the both side of the 3 by h, we will get this one. We will get this one, f z plus h minus f of z divided by h equal to 1 by h integral, this is z to z plus h. Okay, f of w dw, I will get this one. Then again I will subtract from it fz. Okay, minus fz. Okay, then in the right hand side I will make some rearrangement, that is 1 by h z to z plus h. Okay, f of w dw. Then in the right hand side I will divide by h and multiply by the same value h. Then again I will write it in this form, integral 1 by z plus h f of w dw. Okay, this z you should write slightly above, otherwise they are overlapping each other. So this is z. Now in I'm writing this f of z by h integral z to z plus h d of z. You can check it out. If I integrate this, I will get z. Then if I put the limit of the definite integral, I will get z plus h. So that will be z plus h minus z. That will h. I will get this step back. Okay. These are only rearrangement. Then this is dz. You should put dw, not dz. Okay. dw, not dz. Our aim is to apply the continuity of the function. So you should write dw. Only then we can take the integral sign common. So write dw. Then fz is a function, but it is independent of w, so it can be taken outside the integral sign or can be put inside the integral sign. So I am putting this inside the integral sign in the next step. Then I will take the integral and 1 by h common. Then I will write this step. That is, this will be my fz plus h minus fz by h minus f of z. In the right hand side it will be integral z to plus h 1 by h f of w minus f of z dw. Put this equation 4. Okay, is it okay? Now this function, in the statement of the theorem, it is given fz is continuous in the domain D. So using the definition of continuity, the function fz fw fw, this is variable in w, fw, the function fw is a continuous function. CTS stand for continuous, FN stand for function. Do not write this kind of notation in your exam. Write continuous and function in properly. Here I am using the shorthand. The function fw is a continuous function of z. Therefore, for epsilon greater than 0, there exists delta greater than 0 such that f of w minus f of z is less than epsilon. Put this equation 5 whenever w minus z is less than delta. Okay, so since h is arbitrarily small, right, since h is arbitrarily small, because z plus h is any point in the neighborhood of z, so since h is arbitrarily small, h is arbitrarily small positive number, small, so choosing mod h less than delta, so that every point w every point every point w lies in the every point w lies in the line joining z to z plus h satisfy 5. Every point W lies in this line satisfy this condition. Okay. That means f is continuous function of z for epsilon greater than 0. For epsilon greater than 0, we get delta greater than 0 such that this happens, and whenever this happens, okay, we have chosen h arbitrarily small such that a modulus of h is less than modulus of h is also less than delta, so that every point w lies in the line joining z to z plus h satisfy our 5. Okay, therefore and from 4 and 5 we have what is the equation 4? 4 is this one. So 4 is this one. Put the modulus in both side of the 4. We will get this modulus in both side of the 4. Fz plus h minus fz minus f of z modulus. Then in the right hand side, if I put modulus, I will get this one as this is the continuous function. Our given function is continuous function. And take modulus inside the integral sign. F omega minus f of z modulus, then modulus of dw. This is less than delta. So next put the value of this in 5 use 5. This is epsilon. Okay, this is epsilon, so this will give you modulus of fz plus h minus fz by h minus fz. In the right hand side it will be less than 1 by modulus h epsilon. Then again integral over z to z plus h modulus of dw. In the example of complex integral lecture, I have solved this. This value is the length of the rectifiable curve. That is here length of curve will be z plus h minus z. That will be our h. Okay. So this is equal to 1 by h epsilon by this, and which is equal to by epsilon. That means this is equal to my limit. You should write here, since epsilon greater than epsilon is arbitrary 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 positive number, arbitrary positive number, limit h tends to 0 equal to f of z plus h minus f of z by h equal to fz. Right hand side will be nearer to 0, so difference will be equal to 0. This implies f dash z equal to fz. Since f dash z is differentiable, since f dash z is differentiable for all values of z, all values of z in D. So fz is analytic in D, and derivative of analytic function is analytic. Derivative of analytic function is analytic. Okay, function is analytic. So therefore from here f that z is equal to small f z, mean therefore we can conclude that fz is an analytic function. Analytic function in T. With that, I would like to conclude. Remaining will be the next lecture. Thank you.